Looking inside the black box. This is maybe one of the more dangerous talks I've ever given because it's like a little bit of a survey towards a bunch of different interpretability methods. And with deep learning, the black box is a little deeper. And you know, if you gaze long into an abyss, the abyss also gazes into you. And there's a couple reasons this is dangerous, but let's go in. So I was inspired to kind of develop this talk because last year at this same course, Professor Alexander Binder gave a fantastic lecture on his layer-wise relevance propagation method, which he is one of the main developers for. And I loved the talk, but didn't quite understand all of it. So I went back and read the papers and developed a sort of similar talk, and then realized it was the same talk, so I changed it, and now it's hopefully unrecognizable to anyone who might have been at the course last year. So my approach is a little different to interpretability. I figure, why don't we just ask the AI directly how to interpret its predictions? So OpenAI recently released this text generation tool, and I asked it at talktotransformer.com, how can we interpret the prediction of deep neural networks? And this is what it spat out. Deep learning is not perfect, and there's nothing stopping us from improving the algorithm, but the current state in the marketplace implies that the machine learning is being more widely adopted than it has in the past. If you think about it, how important is it to get a computer to do all the computations while leaving the user and content completely unaware of what's going on? This is probably exactly the goal of deep learning. So this doesn't sound right to me. Maybe this was the wrong approach, and we should go to the literature and see what other scientists have done. I don't think the AI is ready yet, but you know, it's getting there. So quick review of GANs. I know we've heard a lot about them today. You start with this latent vector, Z, and we want to have a function g that generates some image maybe from it. So you reshape it into a shape that kind of might resemble an image. Then we stack a bunch of layers, upsample, make it even bigger, add some skip connections, call it a ResNet, do some training. And this big GAN architecture is one of the state-of-the-art GANs for generating data. And this is supposedly a way we can do interpretability, is to generate the data from more or less scratch. So you can ask it to generate, by conditioning on the class label, a butterfly or a cheeseburger, pictures of islands and dogs, and sometimes it doesn't work too well if you haven't trained it enough, and you end up with dog ball here, who is neither dog nor ball. But you get some pretty nice samples out of it. And Big GAN discovered this trick. The latent space of Z, a lot of GAN papers draw from a uniform distribution, but Big GAN used a univariate Gaussian, which we heard Bliss talk about earlier. So I played around with their Colab notebook, which is linked to in this presentation, and generated a bunch of crocodiles and a bunch of chihuahuas. And to try to understand the similarities between them, I interpolated the Z vector between them and generated whatever that is in between. So I'm not sure we're gaining any understanding of how the black box works here, but maybe if you look kind of center left column, foxes are semantically related to chihuahuas and crocodiles. I'm not sure. But what they did discover and explore in the paper is that this truncation trick, if you truncate the Gaussian and don't sample as much from the tails and just sample closer to the mean, you end up with better quality chihuahuas and crocodiles, but less varied. So tried the interpolation here. The foxes are still there, so maybe we're gaining some understanding of biology. Links here. It's tons of fun and super easy to play with. Truncation trick is all you need to understand. So it's hard to evaluate the generator of GANs, whether or not it's doing the right thing. Because ideally, we want to be from the true distribution of the data, but the goal is to try to find it, so it's not super clear how to do this. And the ImageNet, cats and dogs and toasters and airplanes people came up with this inception score where you take some samples generated by your GAN and you pass them through InceptionNet, which is a state-of-the-art computer vision model, and you look at the probabilities of the labels. And so for good samples, you want low entropy in the predictions of the network because you want to be pretty sure of what the image is to say, oh, these are good images. But you also want high entropy in the prior distribution over the labels so that you generate varied samples. So this is one of the quantitative metrics, and if you put this dog through InceptionNet would probably guess like a human that it was a dog, but our friend Dogball here he has a little higher entropy because it's not clear what he is to anyone. So if you take the KL divergence, this is one of the ways to quantitatively evaluate this. Now the Fréchet inception distance is another way that also uses InceptionNet, but instead chops off the end and then puts a bunch of real images in, sees what the activations are at this layer where we've chopped it off, so it's not a classification yet. Does the same thing for generated images, and then you use the Fréchet distance between these two as a kind of quantitative measure of does my network see data the same way. So neither of these measures are really applicable to the kind of data that any of us deal with because InceptionNet is a fantastic model for cats and dogs and toasters and chihuahuas and crocodiles, but it's not clear whether it's the best architecture for healthy controls versus autism in MRI image, or, you know, we don't have that. We don't have a benchmark deep learning pre-trained network that we all compare against. And we have many, many image modalities. So it's a little bit harder, but we heard some ways that you can actually evaluate the generator easier from Bliss's talk earlier. So big GAN, high quality samples. The other really nice state-of-the-art GAN that came out last year is style GAN. And so the style GAN is really the first GAN that changes the architecture of the generator substantially. And normally on the left here, we've got sort of a standard setup where we start with a latent code and we stack a bunch of layers and make it bigger and end up with an image somehow. Style GAN takes a bit of a different approach. So first, there's this mapping network F. So you still have a latent space Z, but then you find a different intermediate latent space W, where hopefully this intermediate space is going to have linearly separable styles that are semantically meaningful and that like actually encode the real features in your data that you care about. So also, there's another pathway in style GAN where they inject noise, like pure noise during training and testing, to model the parts of the image that aren't really semantically related to anything and just related to randomness. And so this is kind of what it might look like if the real features have this distribution where, you know, there's parts of it that there's no data for. So you might imagine that there are far fewer bald women than there are men. So the space of features in a face recognition data set would have very, very few women with shaved heads, let's say, and vice versa, there are comparatively fewer men with long hair. A normal GAN has this kind of mapping that doesn't take this into account at all, and it just tries to learn the best system, and it's uninterpretable in the end. Style GAN tries to make this more related to the real features. And they really generate some fantastic results. even more impressive than the progressively growing GAN that some of the other speakers displayed. And you can see these are all completely synthetic examples. And on each row, you kind of have similar skin tones. And in the columns, you have other semantically meaningful things, like the left column has glasses, the middle column is a young boy, and the column to the right of that is a woman who's looking slightly off to the side. So there's really like a lot that can be modeled here. And so I found this interesting, and I used this technique to modify the smile, and I maybe let it run for a little too long, and it looks a little crazy. But you can also learn different semantically meaningful directions like gender, and you know, if I get more male, I grow a beard, and if I get more female, I get longer hair and dimples, and I think I'm pretty as a female. And I tried this on Ariel too, and he looks pretty fabulous as a woman too, and you know, his hairline starts to recede as he gets more male. And you can see the difference between these two GIFs of the noise channel, where I've randomized it between each frame for me, but kept it static for Ariel. So the background is changing slightly, and the hair position, which is like, you know, not a semantic thing. It's like depends on how long I took to shave and that kind of thing, comb my hair. And I think this is more, we're starting to get a better intuition about the black box now. There is a weakness to the model though, and I tried this with age. I look pretty childish as a young boy, but there is no way I could ever grow such a glorious beard, so there are weaknesses to this style GAN. And I'm using this with some radiologists in my millennial side hustle outside of neuroscience to work on a big mammography data set to try to generate synthetic data to balance classes for some work that we're doing there, which is not finished, but it's still generating some compelling looking data. Can't show you the real images, but they look similar. So I'm not sure we got completely into the black box by using a model to generate data, but let's do a quick survey of the other stuff that's out there and the other ways to interpret predictions. So in terms of understanding the model, activation maximization is a technique you can use to find the input that for a deep learning network maximizes the prediction for one class. And I'm not sure what we're supposed to gain in terms of understanding and interpretability from these images. Maybe this is like the most representative dumbbell, cup, and Dalmatian for I think this is VGG 16. Not sure that this is useful, but you can use a similar technique, Deep Dream, to create some pretty psychedelic visualizations. And this is a surface of my T1 that I've put through Deep Dream, and all I can really tell is that I've got some demons in here. But again, you can go to the URL at the bottom here and generate these fairly easily yourself and play with the systems. So let's try to look at the filters now and visualize what's going on in the black box. The first layer is pretty easy. You can actually just plot the weights, and this is from the AlexNet paper that's come up a few times today. They used to, way back in the day in 2012, use big 11 by 11 convolutional filters for the first layer at least, and this is what the filters selected for when they slid across the image. But if you go a little deeper, you start getting nonlinear combinations of the outputs of these, which very, very quickly become completely uninterpretable. And if we wanted to tell what does this layer do exactly, looking at the weights of these little 3 by 3 filters doesn't really help, especially because maybe there's 32 channels. If we can look at the activations, which gives us sort of a little bit more, but only for this single image that we've put in, and there's still a lot of them. not sure that this is still a useful strategy. So deconvolution is a way to kind of visualize what each filter responds to most strongly over the whole input. And it's basically a collection of hacks to say, okay, let's say I had this activation for this filter layer. It's smaller than the input space though, because we've done max pooling. So let's save the location of where the maximum occurred so that we can propagate this back to the input. And we're still going to lose some information here, but if we do this over and over again, we can get all the way back to the input space. And so for these filters in layer 4, these patches got maximized, activated maximally, and deconvolution kind of on the left here produces this visualization of what the filter sees in these images to make them activate so strongly. So it turns out, though, that if you don't use max pooling in your network, this really doesn't work very well. And it's because of the way they dealt with the rectified linear unit, which are pretty ubiquitous in feed-forward convolutional networks like this. And so normally, when you're doing the forward pass of and trying to make a prediction, negative inputs get clamped to 0 by this ReLU. And in back propagation, this is taken into account because you don't want to update weights that didn't create the signal. So when you get a negative gradient backwards in these yellow squares, you zero out where the ReLU was clamped to 0. But they didn't take this into account for the deconvnet. They just did this backwards zeroing along with their max pooling thing. So this is just a combination of both the back propagation strategy to go through the ReLU and the backwards deconvnet approach. And this produces some nicer visualizations on a wider category of neural networks, and this is sort of the state of the art of how to visualize like what a filter sees in its receptive field when it gets activated strongly. And so you can see on the left here, the deconv are very blurry without the max pooling, but guided back propagation seems to work. So the next way to kind of interpret predictions is to not try to look inside, but try to generate a heat map of what parts of the input were most strongly related to the prediction. And I hesitate to use the word caused because not a lot of this work is about causal inference, but I think that's the goal, is to try to get at causality, what parts of the input space cause the prediction. So a pretty good way to generate a heat map is to do occlusion testing. And it's very expensive, and you basically just take an image, you know this is a Pomeranian, and you artificially occlude every possible part of the image and see how the prediction changes. And the true label of Pomeranian is most certain whenever you don't put this square right over the Pomeranian's face, and then you're predicting dog. You know, it turns out dogs and balls are more semantically related than one might think. So, but this is definitely not how the brain does it, though. There's no demon in my head that's sliding around a gray square when I try to figure out what things are and what parts of objects are meaningful. The other way you can kind of pose this problem is using saliency. So, but this is now a little bit of a different question, and the question now is really, what if we change parts of the input space? How does that change the prediction? Which is maybe, hopefully, related to what causes the prediction, but it's not the same question. And we use this Jacobian matrix, which is in the shape of the input image, And this Jacobian matrix is really just the best linear approximation for the mapping that the network makes around the space of the data point that you're trying to explain. And so if you don't like live in this probability land where gradients are intuitive, it's important to draw this out. Backprop, the way it works is you calculate this loss function by going through your network, and then you take the gradient of your loss with respect to all the parameters of the network. And this is what you normally use derivatives for in this space. The saliency is very, very similar to this, except you're now taking the derivative of the output prediction, so there's no loss function anymore, with respect to the inputs. And you don't care about the weights now because we're not trying to train, but it's very similar. And you can use this to make really pixel-dense heat maps. And so for the dog on the left here, the visualization below, the bright pixels are where, if you change those pixels, the prediction of dog changes most strongly. And sailboats usually are on water if you're doing it right, and so it highlights the sail, but also the water. Whereas the visualization of this jackfruit, I think it is, or something on the right is a little bit more diffuse because it's occluded and it's kind of harder to see. Now the problem with saliency, though, is that if you asked on the left for what are the salient parts of the image to predict a cat, you would end up with a very, very similar visualization. And if you start changing the pixels, you can end up with a completely different heat map. So this is maybe not ideal. And we want to know why the network thinks this is a dog and not just all the possible animals. So another way to do this is class activation mapping, where now you're going to change the structure of your network to include this last linear layer. So in deep learning, we generally love all the nonlinearities we can possibly cram in there. But to interpret, we need something linear, because I think this might be how we operate, as we linearize everything around us. So class activation mapping takes the last convolutional layer and introduces this global average pooling operator, where you take the activation across the whole spatial configuration of the receptive fields that made each filter fire, and you average that all, and then you learn a weight in this next linear layer, and then you can produce heat maps for each of these last layer filters, and if you add them all together, this localizes the Australian Terrier quite well in this image. And actually, to come up with the final probability, you just sum this heat map. The problem with this is that it generally decreases the accuracy of the network, which we don't want. But it does give you a pretty good localization. So we're going to put a bunch of this together, and GradCam picks up on this class activation mapping. And so we've got a sort of vanilla convolutional neural network here. It's predicted cat, and we've got this last convolutional layer, but now we've got some fully connected units here that are pretty common in these kinds of architectures, and we can't do the same kind of global average pooling here, because then these nonlinearities don't work. So instead, we're going to take the derivative of the softmax with respect to all these filters, and then we're going to global average pool that. So it's sort of a combination of a saliency, but not with respect to the input, with respect to this last convolutional layer, and then we're going to multiply those by the feature maps themselves, which we don't have to global average pool directly now. Add them all up, put them through a rectified linear unit, and that's GradCam. And so here, this is where the network thinks the cat is. And this is a hard example because there's also a dog in here. So we ideally want to be able to come up with a prediction that separates the dog and the cat as different things. But this is still a little blurry, and so if you guide it with guided backprop, which produces pixel-dense but not class-specific heat maps, and you multiply these together, you end up with a pretty good pixel-dense, class-specific localization for the cat. And they show that this, for this one example, works quite well. The dog and the cat produce different heat maps, as we expect they should. The dog's up here, the cat's down there, and the occlusion map sort of lines up pretty well with where they predict. Now, I've tried to use this in some never-ending quality control of MRI images, and for this example, I think I might be able to convince myself that maybe the network is learning that there's a signal-to-noise ratio that you can pick up in the empty space outside the brain, and if it's pretty clear, that the image is more likely to pass. And the fail image, there's lots of motion artifacts in this, so it picks up on that in some brain areas, but also in the empty space. But really, yeah, I've heard anecdotally that either it works really well and it generates what you expect it to generate, or it doesn't. And it's hard to say when it's right and when it's wrong. And this is tough. So these methods all fit in with the kind of sensitivity with respect to the inputs. But the problem with GradCam, the big problem that Alexander Binder raised, is that they don't model negative evidence at all. So I think most neural networks and most human networks would pretty easily identify that there's lots of positive evidence for horses in this silhouette. But if you change the image just a little bit and add a little bit of negative evidence, now it's pretty clear they're unicorns and not horses. And we want our interpretability method to maybe be able to model this properly. So this was one of the major motivations he gave to layer-wise relevance propagation, where you take a trained neural network and you basically run it backwards, but differently than backprop, by propagating the relevance of the prediction from layer to layer, and it uses these principles of conservation, so relevance can't just appear out of thin air at a layer. It has to be constant all the way to the input. Has to be positive, even though it can model negative evidence. Has to be continuous, so if you change the input slightly, the output shouldn't change that much. And if you remove relevant features from the input, it should reduce the prediction accuracy, which, I mean, these principles all sound pretty good to me, except maybe the continuity one, because, you know, those unicorn horns are pretty small perturbations. And also, layer-wise relevance propagation, there are quite a few hyperparameters in how to propagate through the different kinds of nonlinearities, and what to do with the max pooling and the global average pooling and that kind of thing. And yeah, so there is a ratio of positive to evidence and to negative evidence that you need to use by this alpha and beta parameter. And there's starting to be a lot of these interpretability methods, and I think it could be pretty easy to just kind of try all the combinations until you get a heat map that agrees with your theory, and then you're maybe overfitting your explanation, which we try really hard to not do in the training phase, but I think this is a real risk that not a lot of people are thinking about. There's another method called LIME, the Local Interpretable Model Agnostic Explanations, which has a great GitHub package. And basically, the approach here is to approximate some nonlinear, complicated decision function just locally, just within the space of a single training example, and come up with a simpler model that's going to be a good approximation. We're going to optimize so that we find the best interpretable model G that explains the real model F with some proximity measure that defines what's local and a penalty on complexity. It's all very mathy, but graphically it sort of makes sense if your space and your decision boundary is this blue and red region, and it's hard to come up with a function for this, pretty nonlinear. But for this red cross, this straight line, the dotted straight line, is a pretty good linear approximation to what's important local to that example, whereas a red cross over here that explanation might not hold at all. So basically, you have to generate data to fit this this interpretable model using your proximity measure. And in practice, if you go to their GitHub repository, where this is like 2 lines of code that you can add to any machine learning classifier or regressor, this is what they do in practice. So they just say linear models are going to be interpretable models. We're just going to use the negative exponential of Euclidean distance as a similarity measure, and complexity penalty, we're just going to choose k features. So this nice mathiness sort of disappears in the GitHub implementation, where it's just sort of they implement feature selection for images, which is not clear, and they take the squared distance to optimize a linear model to fit what the actual model is around the space. So I used this in this defacing detector, which apparently now is not sufficient to detect if an image has been sufficiently anonymized, because now we can reface images with GANs. But if you try out Lime on this, what it actually does under the hood is it groups pixels together into superpixels, where it kind of uses a proximity and intensity to kind of come up with blobs. So I just ran it with defaults here, and so this explanation on the right is the areas that Lime thinks contributed to the correct decision that this MRI image still has a face and is not ready to be shared in the BIDS validator. So it sees part of the face, but it's also picking up this part of the image, and maybe this superpixel approach works for images of cats and dogs and toasters, but is not valid for MRI images or diffusion maps or what you're going to use this for. So this is why it's dangerous, because the GitHub repository is super easy to use. This is literally like 4 lines of code, but you should maybe be careful before you put this in a paper as explaining causal inference, because there's a lot of assumptions built into all of these methods. So now we've kind of gone over a pretty good sampling of many of the methods that are out there. If I had to recommend one or two, I would pick Lime and GradCam, just because they're super easy to apply to your machine learning. And GradCam really is deep learning specific, but Lime you can use on anything that's machine learning. But you should read the papers if you are going to use them and understand the limitations to the methods. I don't think this is a complete kind of chart of how we can look inside the black box. I think you can design networks interpretably, and so like there's this work showing that spatial transformer networks can be used as kind of like a module of your network and spit out 6 parameters that you apply as a affine transformation to your input, and it just learns registration. So that's like pretty interpretable. There's also ways you can look at the properties of your layers. You can tie weights and build in rotational invariance at different levels, which may or may not be a good things to do, because you might want to do this to make sure that you don't have to do registration, but it's pretty unlikely that the ventricles are going to appear flipped within a brain, or you're going to end up with the corpus callosum halfway across one of the sides of the brain. So you want to make sure that you understand the properties of convnets and GANs and these interpretability methods if you're going to use them. So there's also all the attention stuff that Grace Lindsay presented earlier, which I think is a strong avenue of research, and there's lots of work being done in different directions on this. But I am out of time. So there's also significant confusion as to what interpretability even means. I kind of intuitively think of it, I want to get at causal inference, but you can also talk about it in terms of transparency, simulatability, and there's a great paper by Zach Lipton called The Mythos of Model Interpretability, where he kind of reviews a bunch of the different things we mean by interpretation. So these are kind of the easiest to get up and running with GitHub repositories that are fairly easy to implement on your own. Even if you're not training models yourself, even if you're a total beginner, it's fun to play with, and you do get an intuition just by playing around with other people's code. And I encourage you to go for it. So I don't know if I've given you all of the tools to look inside the black box, and I really want to drive home the message that it is a dangerous thing to try to apply these methods, but I think it is something we need to talk about if we're going to use deep learning to try to do science, because if we can't come up with explanations for why these amazing function approximators are doing the things that they're doing, then maybe we should just leave them alone to the computer science crowd and go back to statistics and try to be rigorous and not just trust in the machine. So thanks a lot. That's all I got, and I'm happy to take your questions.